Hello there, this is a geometry video. It is chapter 11, section 2, and today we're going to continue our journey with areas of different figures, and we're going to focus on trapezoids, rhombi, which is just plural for rhombus. Instead of saying rhombuses, you would just say rhombi, and kites. And for the area of a trapezoid, which is the first step, we have a formula that, again, you probably already know is area equals 1/2 the sum of both bases times the height, but you probably didn't know where it came from. So I want to show you very quickly, again, kind of what we did with the triangle. And what I've done is I've tried to basically, here's your first trapezoid, which has the first base on top, and then base 2 is on the bottom, and then you have your height. And what you do is if you basically take the exact same trapezoid and kind of rotate it, flip it over and kind of put it together with the other one, then you basically have, again, a parallelogram. And the area of a parallelogram, we already said before, was base times height. And this time, when you look at this parallelogram, it ends up being, the base of the parallelogram ends up being base 1 plus this is base 2. So this distance is the same as the base 2, which was down here. So either way you look at it, this is the same thing as B1, this is the same thing as B2. So you take the sum of the bases and then multiply it by the height to get the area of the parallelogram. But again, you only want the area of one trapezoid, so you end up taking it times 1/2. So just in case you were curious about where that came from, there you go. But nonetheless, this is our formula, so we're going to get right to it. Example 1. One of Brianna's trapezoid-shaped totes is shown. And trust me, I only drew the bare bones of the diagram in the textbook, but if you want to look at her handbag, you can. Find the amount of material used to make the side shown. So basically they want us to see how much material would have to be made if, to make this, this tote bag, right? So basically we need to use our formula because it's a parallelogram, or sorry, because it's a trapezoid. We want to go area equals 1/2 the sum of the bases. So this base here is 28 centimeters, and then the second base is 58 centimeters, and then the height is 30 centimeters. So not a very complicated problem. Everything was given to us. All we have to do is plug it into our formula. So we're going to take 28 plus 58, and that's going to give us 86. And then one thing that I noticed that students kind of get confused with sometimes is they want to kind of take this 1/2 and then divide both of those by 1/2. You don't want to do that, but it doesn't matter which one you divide. You could take 86 and divide it by 2, which would give you 43, and then times that by 30. Or you could take 30 divided by 2, which is 15, times 86. So in either case, you're going to get 1290. Both 43 times 30 and 15 times 86 are equal to 1290, either way that you do it. Now what would be bad is if you divided both of those by 1/2 and ended up with 43 times 15. That would be a problem. Okay, so we get 1290. So it says the amount of material that you would need is 1,290 square centimeters. Alrighty, so now we're going to let you do this do-it-yourself question, and then we're going to go on to example 2. In example 2, it says, Emilia designed the pennant, and again, there's a lot more in the diagram on page 790. If you care to look at it, I only drew the parts that were pertinent to the problem. But this is her pennant that she's designed for her team. And they want us to find the area of the shaded portion, which is a trapezoid. All right, so we want to do base 1 and base 2 and then the height. But the problem here with this little guy is that they haven't given us the base. Now remember that in a trapezoid, the bases are always going to be the parts of the trapezoid that are parallel. So these are your bases, okay, the 10 inches and then this piece right here. But they didn't actually tell you what that piece was. So you can kind of draw yourself a little rectangle like that, and you know that this is going to be 90 here, and this is going to be 4 inches. All right, and then you have the hypotenuse, and what you don't know is this piece. You know that the entire length is 10 inches, but you don't know the length from this point on. So what we want to do is kind of use Pythagorean Theorem to help us figure that out. So we have one of the legs is 4. We don't know what this piece is. We're going to go ahead and call that x. But we know the hypotenuse is 8.5. And so we're going to subtract 16 from both sides because 4 squared is 16. And then 8.5 squared is 72.25. And we're going to subtract 16 from that, and you're going to get 56.25. And we square root both sides, and x will equal 7.5. So it turns out that this top portion is 7.5, which means that this bottom portion is 10 minus the 7.5, which is 2.5. So if this is 2.5, then so is this piece. And now we have the pieces that we need to plug into our area formula. So our area for the trapezoid is going to be 1/2 the sum of the two bases. So the bases are going to be 2.5 and 10, thanks to our Pythagorean theorem. And our height, because you want it perpendicular to the bases, is going to be the 4 inches. So now I'm going to take the 1/2 and the 4, which is 2. So 4 divided by 2 is 2. And then 10 and 2.5 is 12.5. So 2 times 12.5 is going to be 25 square inches. So for example 2, you get a total of 25 square inches. Alrighty? And then we're going to let you do this little guy. Now again, these are supposed to be some earrings. If it doesn't look like an earring to you, I'm sorry, but you can probably look in your textbook on page 790 if you want a better picture. Alrighty? So now we're going to go to our second concept here. We did say in the beginning that the area of, we're doing areas of trapezoids, rhombi, and kites. So lucky for us, the area of a rhombus and a kite actually ends up having the same formula. So the formula for finding the area of a rhombus or a kite is for you to take 1/2 diagonal 1 times diagonal 2. And so diagonal 1 in this case would be the diagonal from there to there, and diagonal 2 would be there to there. One of those diagonals are perpendicular to each other in both scenarios. But again, the formula is to take diagonal 1 times diagonal 2, either in the case of a rhombus or the case of a kite. Now you know that in a rhombus, all 4 sides are the same. In the case of a kite, then that is not the case, but usually have adjacent sides. So you have 2 pairs that are the same. So these 2 will be the same, but they're not opposite sides. They're actually adjacent sides. So there's no opposite sides congruent in the case of a kite. But the area is going to be 1/2 diagonal 1 times diagonal 2. So we're going to apply that to our example here. Example 3 says find the area of each rhombus or kite. In part A, we appear to have a kite. In part B, it is a rhombus. And we can see that because we have the diagonals that are congruent here and then congruent this way as well. So what we need to do is, in this case, it's real simple. We just need to plug it right into our formula. Diagonal 1, it tells us, is 15 meters. And diagonal 2, it tells us, is 8 meters. So we're just going to very quickly take 15 times 8, which is 120. And divide that by 2, which gives us 60. So the area for part A is 60 meters squared. That complicated. For part B, we need to do the same thing. However, in this case, we need to double our diagonals because this is telling us that this is 12 feet, but the entire diagonal is twice that, so it would be 24 feet. And same thing is here. This is 10 feet, which would make this also 10 feet, so 20. Alrighty, so we're going to get 24 times 20, which is 480. And then we're going to divide that by 2, which will give us 240 square feet. Alrighty? So that is how you do that. So we will let you do these two examples, or these two figures, part of the same example, and then we will go to our last example for today. It says here, one diagonal of a rhombus is twice as long as the other diagonal. If the area of the rhombus is 169 square milliliters, what are the lengths of the diagonals? So we don't actually have to draw a rhombus. You could if you want to, but we don't actually need to draw it. All we know is that all we need to know is that we have area equals 1/2 diagonal 1 times diagonal 2. So if I say diagonal 1 is equal to x, for example, it says one diagonal of a rhombus is twice as long as the other. So that would mean that diagonal 2 would be twice as long as the other one. Does that make sense? I hope that makes sense. So basically, if I call one diagonal x, the other diagonal is twice the length. So if this one was 10, the other one would be 2 times 10, which is 20. If this one was 5, it would be 2 times 5, which is 10. If this was 50, then it would be 2 times 50, which is 100. So that's basically what they're telling us. So all I have to do is, know that the area is 169 square milliliters. So I'm going to replace the area with 169. And then I'm going to put, in the place of diagonal 1, we're going to put x. And in the place of diagonal 2, we're going to put 2x. So now I'm going to get 1/2 times 2x squared equals 169, but the 1/2 times 2 is going to cancel, and you're going to get 169 equals x squared. The square root both sides, and x equals plus or minus 169. Sorry, plus or minus the square root of 169, which is 13. But again, because this is a real life application, we don't want to do negative 13, because that would mean that the diagonal was a negative 13 length, and that doesn't make any sense. So we're going to stay with the positive 13, and we were talking about milliliters. So we're going to leave it at that. So we get, the diagonal is 13 millimeters. Sorry, it's not milliliters, it's millimeters. So sorry. So that would mean that this little guy should have been millimeters. And this little guy, I thought that was weird that they were using milliliter, which is usually for fluid. So that was kind of strange. But it's 13 millimeters. My bad. And then they want you to say the lengths of both diagonals. So the first diagonal is 13 millimeters. Then the other diagonal, which is 2 times x, would then be twice that, which would be 26 millimeters. So your diagonals are 13 and 26 millimeters each, respectively. All right? So now we're going to let you do this last do-it-yourself question, and once you have completed this question, you will have completed your notes for this lesson, and I will see you in class, and thanks for watching.